Good day, Sir Azri. We are from Group 2, and the name of our group is Power Nexus. My name is Heli Adria Hapindra, and I will be presenting the first part of our integrated power system design for a remote palm oil facility in Sabah. This facility is disconnected from the national grid, so it requires a reliable and independent power source. Our solution is a hybrid system utilizing Sabah hydro and solar resources to power both the facility and a nearby village. Our goal is to cover everything from generation design and energy storage to transmission safety and motor control using VFDs. Now I will talk about the proposed hybrid generation system. The primary source is a small hydroelectric generator which uses a dam to capture hydraulic energy from water stored in a reservoir. The potential energy converts to kinetic energy as the water flows through the penstock. A turbine converts kinetic energy into mechanical energy driving an AC generator to produce electricity through electromagnetic induction. Because the water flows varies, rectifier converts unstable AC into steady DC. Inverters then convert it back to stable AC, ensuring it matches the solar output for safe combination at the distribution panel. The secondary source is a solar PV array, which harvests solar irradiance using photovoltaic cells protected by the glass and metal frame. The photovoltaic cells absorb sunlight to trigger photovoltaic effect, exciting electrons to produce direct current electricity. A solar inverter converts this DC into AC to match standard appliances and industrial motor requirements. Next is the load demand estimation. For the industrial load, we are required to power crude oil extraction motors, mixers, digester, conveyors, and facility lighting. As for the village load, we need to provide electricity for 20 households, covering appliances like television, refrigerator, and washing machine. The hybrid generation system is designed to support a combined daily consumption of 5,579.8 kilowatt-hour per day. For the generator sizing, the hydropower output it needs to generate 167.751 kilowatt, which is approximately 4,026 kilowatt-hour per day, based on the 0.9 flow rate and 100 meter net head. For the solar power, it required capacity of 1,630.4348 kilowatt to cover the daily power deficit that is not met by the hydroelectric generator. Both power source and the energy storage system are managed and integrated within a central control room. Next is the load balancing and energy storage. Firstly, we will talk about the load balancing strategy. Firstly is prioritization. Critical industrial machinery for oil extraction is prioritized. Non-essential load are automatically reduced during periods of low generation. The second one is operational scheduling. High-energy industrial processes are scheduled during peak sunlight or high water flow to maximize direct use of the generated power. And third is equilibrium. The system will constantly maintain a balance between production and consumption to prevent grid instability. Moving on to the energy storage system, the hardware consists of 450 units of 48 voltage, 200 ampere-hour live pure for batteries. The total capacity required is 4,316.04 kilowatt-hour, providing 2 days of energy autonomy. The advantages is that it is selected for being maintenance-free, lightweight, and offering high stability for a long lifespan.
Good evening and hi, my name is Ifzur Rashid bin Abdullah and I will be presenting section 3.0, that is transmission and distribution. Our engineering goal was to design a network that delivers power from the palm oil mill to the village efficiently, while strictly complying with the Electricity Regulation 1994. First, let's discuss our voltage strategy. We generate power at 415 volts, however, to minimize massive power losses over the long distance, we step this up to 11,000 volt. We choose 11,000 volt because it is the standard TNB medium voltage level for rural areas. Higher voltage reduces the current, which significantly lower resistive losses in the lines. For the physical infrastructure, we selected specific conductor for each section. For the 11,000 transmission line, we use SCSR, aluminum conductor steel reinforced. The steel core provides necessary strength to span long distance between poles. For the village distribution, we switch to ABC aerial bundle cable. Since these lines run near homes, the full installation prevents short circuit, protect villagers from accidental electric shock. Moving on to slide 2, that is transformer selection, which is the most critical part. We calculate the village daily energy usage, roughly 3,993 kilowatt-hour. When average over 24 hours, the continuous load is only 166 kilowatt. However, we select 500 kilovolt ampere transformer, which is give us 400 kilowatt of real power capacity. We choose this larger size to handle peak demand. Village electricity usage spikes heavily in the evening. Our choice provide a 2.4 times safety margin, ensuring transformer never overheats during those critical hours. To ensure reliability, we implement a layered protection scheme. First, lightning arrestor to divert high voltage surge safely to the ground. Second, drop out fuse on the 11,000 side. Automatically isolate the transformer during short circuit. And third, a solid earthing system strictly follow TNB standard to ensure safety. Finally, the single line diagram on the right summarizes the flow. Power starts at the hybrid generation and step ups for efficient transmission, then step down for safe village distribution. This guarantees supply that is just as reliable and efficient as the national grid. Thank you.
Hello sir, my name is Ahmad Khairi bin Roslan, and for my part, I will talk about SC motor selection and control. So the motor we have chosen is G-type COF NEMA Design D. This motor has a very high slip, which is between 5 to 13%. It can effectively reduce the peak load and the volatility of the pumping unit, which give benefit to the safe operation of the beam pumping unit. This flexibility of a high slip motor allow it to protect vital parts such as the sucker rod. Furthermore, it has a low starting current. The operation is in a remote area, so the operation work in a long distribution line, which can cause a quick surge and result in huge voltage loss. So it requires a low starting current motor to prevent excessive voltage drop. Moreover, it can protect the sensitive equipment. If we choose high starting current, it can cause motor windings to generate a large amount of heat in a short time, which cause the sharp rise in winding temperature. Lastly, this motor has a very high lock rotor torque. Both operations require this feature to overcome the massive physical resistance of starting heavily loaded machinery from a complete stop in this location, including high static inertia. It is also managed loaded starts. The motor must immediately lift the weight of the entire column of oil in the well as soon as it's starting turn. Next is the motor ratings. The range of horsepower is between 3 to 125 horsepower. Standard speed between 900 to 1200 RPM, and voltage rating for motor is 415 volt. This is a common range for NEMA Design D motor. Next, starting method. Auto transformer is the best choice for remote location. In this method, the motor starting current is limited by employing a 3-phase auto transformer to reduce the first applied voltage to the resetter. The advantages are it reduces the starting voltage, which causes the starting current to reduce too. Other than that, it has less mechanical stress since it reduces the mechanical stress on the motor and load. On the other hand, the advantages are a higher cost and it is more complex to establish and maintain. Protection scheme. A 3-phase motor protection relay works to evaluate all 3 phases continuously to detect both phase disconnect and phase unbalanced condition. Next, thermal overload relay are intended to offer electromechanical protection to motors against overloading caused by high input current from the main circuit. Last but not least, using instantaneous overcurrent protection that prevent important part and conductor from overheating, which help to prevent fire and injuries. And for my last part is the power electronic drive for speed control and efficiency. We choose one of the technique of variable frequency drive, VFD, which is pulse width modulation, PWM. It includes turning on and off the motor's power source at high frequency, resulting in pulses. PWM provide for precise control of motor speed and torque while optimizing energy consumption. By controlling the pulse width, a VFD may offer exact power output, ensuring that the motor runs smoothly under varying loads and conditions. This method greatly minimizes power losses when compared to standard control system, making it an effective alternative for industrial and commercial application. PWM also improves the efficiency of the motor. PWM's ability to adjust the duty cycle is a critical feature that enables effective regulation of power delivery. By adjusting the duty cycle, the drive changes the average voltage and current given to the motor, allowing for optimal speed and torque control with great efficiency because power loss in the switching transistor is minimized. That's all from me. Thank you.
Hello sir, my name is Sean Javier and my part is about the power electronics integration. And I will be explaining about the design flow of our system through the block diagram that I've inserted in this slide. Okay, so because this facility is completely off-grid, we can't just rely on the TNB lines. So we need to manage the power flow ourselves. And as you can see in the middle of the block diagram, which is the 415 volt main bus, that is the main component or the heart of our design. And we have integrated three key pieces of tech here, which is the first one is the solar. So since the sun isn't constant, we use an MPPT converter, which is a maximum power point tracking, to grab every bit of energy that we can, and then it's connected to an inverter to sync it perfectly to the hydro generator. Next is the energy storage. We use a bi-directional converter. So since it is bi-directional, it can go back and forth. So which means that it automatically pulls in power during the day or when it is sunny, and during the night the power is pushed back out. So there will be no manual switching needed. Finally, for the heavy machines, we didn't just wire them directly, but we use VFDs or variable frequency devices to isolate them, which I will explain on the next slide. So the reason why we design our system this way, it comes down to three things, which is efficiency, stability, and safety. So for the first part is efficiency. By using the VFDs or the variable frequency devices on the pumps, let us control the speed electronically. Instead of using mechanical valves to choke the flow, which can waste a ton of energy, we just slow down the motor. That saves us around 20 to 50% on power. Next is the stability. The two-way battery converter I mentioned, which is the bidirectional converter, it acts like a shock absorber. If a big machine starts up and spikes the load, the battery instantly injects power to keep the voltage steady. So there will be no flickering lights when a big machine is switched on. And the third is the power quality. Since we're sending the power to a village, it has to be clean. Our inverters use LCL filters to strip out or to filter the electrical noise. Not just that, by using these LCL filters, we meet the IEEE 519 standards and don't damage anyone's home appliances. So essentially, the system isn't just powerful, it is also smart and safe. That's it from me. So I will pass this presentation to the next person.
Hey everyone, we'll be going into system analysis 6.0. 6.1, load flow and power balance. For the load flow analysis, the total daily energy demand of the system is about 5,579.8 kilowatt hours. The small hydro plant acts as the main base load source and supplies approximately 4,026 kilowatt hours per day. Solar PV and the battery energy storage system supports the remaining demand, especially during peak hours and at night. A bidirectional converter is used to ensure stable voltage and frequency at 415 volts AC throughout operation. Now, 6.2, voltage stability and power quality. Because this is an off-grid system, voltage stability is very important. Variable frequency drives, or known as VFDs, are used to reduce motor starting current and prevent voltage drops during startup. The battery system provides fast support during load changes. Harmonic filters in the inverter and VFDs ensure that harmonic distortion remains below 5% in compliance with IEEE 519 standards. 6.3, system efficiency and energy optimization. System efficiency is improved through the use of hybrid hydro-solar configuration, which maximizes renewable energy usage. Variable frequency drives, also known as VFDs, allow motors to operate based on actual load demand, resulting in energy savings up to 20 to 50%. And in addition, maximum power point tracking ensures that the solar PV system operates at optimal efficiency under varying conditions. And finally, 6.4, safety, reliability, and environmental impact. Electrical safety is ensured through the use of overcurrent protection, overload protection, and phase failure detection. Transformers are used to provide safe voltage levels for both transmission and end users. By eliminating the need of diesel generators, the system reduces carbon emissions, noise pollution, and overall environmental impact. And in conclusion, this project presents a hybrid off-grid power system design for a remote palm oil processing facility by integrating small hydros, solar PV, and battery energy storage. The system provides a reliable and efficient power supply. The design improves energy efficiency, enhances power quality, and supports environmental sustainability, Overall, this system can serve as a suitable model for similar remote industrial applications in Malaysia.